Welcome to Design High Availability in Campus Networks. We have a lot of different technologies available to us in campus design that can help us improve the resiliency of our networks. And in a lot of cases, when we're just doing the configuration of networks instead of the design elements, we take for granted that some of these things are configured, like first-hop redundancy protocols and taking advantage of nonstop forwarding and stateful switchover, NSF and SSO. But if we're going to design networks, we need to know in more detail what we can do with these protocols. So come along with me as we explore all the different ways that we can improve high availability in our campus networks. And with that, I will see you in the next video. What comes to mind when I use the words network redundancy? Is it a network diagram with a bunch of switches and routers all connected at full mesh? Because if so, I mean, that's great. That's the start of the conversation, but it's not the end of it. In this video, we're going to explore a lot of the foundational conversations we have to have around network redundancy, which is more than just how we connect the devices, but involves also the protocols that we're going to run over our network architecture. Let's dive in. The key to network redundancy is identifying the fact that what we're trying to do is keep the network online, which sounds obvious, but how do we do that? How do we go about creating a redundant network architecture? And one of the fundamental concepts of network redundancy is going to be identifying single points of failure in our network. And this might be trickier than we think. For example, what if I draw a network diagram that looks something like this? I've got an access layer switch, I've got a distribution layer switch, and these are connected. And then I've got a PC down here, maybe it's a client PC or a server, and it's connected to this access layer switch. And then maybe we have the internet coming in up here that's connected to the router. And so we've got a circuit to the internet, and we've got a cable between the router and our distribution switch. So let's say our goal is keeping this client connecting out to the internet at all times. If that's the case, what are the single points of failure in our network? And at first, our eyes are going to fall on the larger objects in this network diagram. For example, if this access layer switch were to go down, we would lose connection to the internet. Same with this distribution layer switch. If that distribution switch went down, we'd lose access to the internet. And hey, guess what? This router up here, that's a single point of failure as well. And yet there are at least 5 other single points of failure on this network. What are they? Well, we have a single circuit to the internet. That's a single point of failure. We have a single connection between the wire and the distribution switch. We have a single connection between the distribution and access switch. And yes, the single cable between an access layer switch and our end device, that is a single point of failure. But it gets even better than that because we have a network interface card on this wired client. That NIC is a single point of failure. Even if everything else in the entire network stays online, all of these red arrows are up and life is good, and this NIC has a hardware failure and goes down, well, that client can no longer speak out to the internet. So the next question we have to ask is, how do we eliminate these single points of failure? And for that matter, should we eliminate those single points of failure? Now you might be saying, well, Jeff, of course we'd want to eliminate all single points of failure in the network, but do we really? Do we really want to have 2 connections between our end client and the access layer switch? And furthermore, if we have a second connection, shouldn't that go to a second access layer switch? Does that make sense in this environment? Well, we have to evaluate a couple of things. First of all, what is the criticality of this particular device? Does it belong to an intern or does it belong to a CEO, for example? And generally speaking, do we want all of our clients to have 2 connections upstream? Because if all wireless clients in our environment have 2 upstream connections to 2 different access layer switches, well, that's going to involve 2 times the cable runs in our walls and 2 times the number of switches that we have to procure in the access layer. This is a level of redundancy that oftentimes does not make sense in our environment. And this brings us to a very important component of any network design, and that is properly evaluating risk. Many conversations around network redundancy is going to come down to a risk evaluation. When we're doing an evaluation, we're going to weigh 2 key concepts. First of all, we need to weigh the impact of whatever it is we're talking about, some kind of network outage. And as part of that, we need to consider the likelihood of this event happening. And next, we need to weigh that against the cost of mitigation. So what do I mean by this? Well, first of all, the impact might be extremely high. For example, if the building gets wiped out by a tornado, then our network is going to go down and we will not be able to conduct business. That would be a high impact event. However, the likelihood of this event is extremely low. Now let's say that we decided that we're going to build a second network architecture, an entire network infrastructure that's just dedicated in case our main building goes down. And in order to do that, it's going to cost us $3 million. Well, $3 million US dollars to some companies is a whole lot of money. To other organizations, it's not a lot of money. And so we have to decide, is the cost of mitigation worth the high impact but low likelihood event of us losing our primary building? Now compare this conversation with the idea of our building losing electricity. If we lose electricity, it's the same impact because our network has just gone down. but the likelihood of this happening is probably greater than us getting hit by a tornado. If we could, for example, pull a second circuit into our building and have redundant UPSs and keep everything online in the event of a power outage, and we could do that for a mere $100,000, well, hey, $100,000 compared to $3 million, that's a whole lot less cost, and it's probably worth it for us to spend these dollars on a high impact and medium likelihood event rather than spending 30 times the amount of money on a high impact yet low likelihood event of happening. I will tell you that we in the networking world, as network technicians, we are guilty of foregoing this conversation. We want to look at this network that we've drawn on the right, excluding the second access switch, and just be aghast at the horror of the fact that we have a single distribution switch. What in the world kind of network is this? Let's get a second distribution switch in there and have the redundancy. And we don't want to have this conversation down here on the left about whether it even makes sense to do that. We get so locked in onto how a network should be designed compared to how it really needs to be designed. In a lot of ways, this comes back to this concept of being book smart versus street smart. And the danger of taking this course at CBT Nuggets and the danger of going through Cisco's process of getting ENSLD certified is that we get so book smart that we forget the fact that we need to be business savvy. We need to have this conversation with our business leaders because at the end of the day, it doesn't make sense to spend an exorbitant amount of money to mitigate a risk that either has a low impact to our business or a low likelihood of happening. Instead, we need to be street smart. We need to think about how things are in real life. We need to take all of the lessons that we're learning here, which, just to be clear, these are good, solid topics to be taking away from the ENSLD conversation. But the engineer who can take what we learn in this course and apply it in real life scenarios, that is the engineer who's going to be a success and become a network architect. So what kinds of conversations are we going to be having throughout this course? Well, first of all, we need to think about how we are going to connect our network devices. So yes, fundamentally connecting our devices is going to matter. For example, are we going to use a partial mesh? Are we going to do a full mesh? Are we going to use hub and spoke, for example? And also, what kind of loops are we going to build? So for example, let's say we have a single distribution switch and we've got a single access layer switch down here, and we're ready for more redundancy in our network. And so what are some ways that we can achieve that? Well, first of all, we could just double up this connection and talk about ether channels to make that connection more robust. Or yes, we could deploy a second distribution switch, having that risk mitigation conversation, making sure that the cost of a second distribution switch is worth the likelihood of our other distribution switch going down, as well as the impact being high enough to warrant that cost. Well, at that point, we're probably going to want a full mesh of connectivity among these devices. But here's the other question. What if we have another access switch in here? Well, how are we supposed to connect these four devices? And one of the concepts that we're going to see in network design has to do with squares versus triangles. And generally speaking, in network design, we absolutely want to favor a triangle design. And what that means here on the left is that rather than connecting all four of these in a square, or even connecting them in a square with a full mesh, this would be a true full mesh connection among all of the distribution and access layer switches. In most cases, we're going to want to build triangles. So let's say we build, and I guess we're still using ether channels down to the first access switch, but then we connect down to the second access switch from those distribution switches. We do not need these access switches to be connected to one another. And the primary reason for this is because the complexity of running protocols on top of this environment is not going to be worth the likelihood of us losing both of our upstream connections such that we need to go through another access switch in order to gain access to the distribution layer. And at that point also, we're going to have bandwidth concerns on those other links. So it's not just complexity, we might need to invest in additional infrastructure, additional cabling, additional ether channels, etc., to make sure that we have enough bandwidth to run multiple access layer switches worth of traffic in this environment. So no, we're not going to use squares in our network design, we're going to use triangles as much as possible. The next question, and one we're going to spend more time covering about later on in this course, is what are these connections right here from a layering perspective? Are they layer 2 or are they layer 3? If they're layer 2, then we're going to need to make sure that we have spanning tree protocol running and configured and tuned, and that can be complex in its own right. And if it's layer 3, we're going to have to run an IGP, maybe OSPF or EIGRP or some other routing protocol in order to make sure we have a fully converged environment. So there are pros and cons to both layer 2 and layer 3, and we need to take those into account. Again, we will be discussing that in more detail later on. But let's assume that we do have layer 2 connection, which is how most access layer designs are out there in the real world. Well, if we do have layer 2 connections, then we're going to have SVIs, a bunch of SVIs, on these distribution switches. SVIs are switch virtual interfaces, and in a lot of cases we call them VLAN interfaces. So on a Cisco switch, you'd get onto a switch, and you'd say interface VLAN 10, for example, and you'd configure an IP address. And this is going to be the default gateway for VLAN 10. But again, we want redundancy in this network, and so we're going to deploy VLAN 10 interfaces as well as other SVIs onto the second distribution switch as well. But because we can't have duplicate IP addresses in the environment, one of these switches might be .1 on the subnet, and the other switch might be .2. And if the default gateway down here is configured to be .1, well, now we have a scenario where we could lose a distribution switch like .1, and clients will go down. Even though we have all of this redundancy in the network, we have a second distribution switch online, but the clients themselves are not looking for .2 as the default gateway. And so in those scenarios, we're going to want to leverage a first hop redundancy protocol, or FHRP. The FHRP is going to use a virtual IP address, let's call it .3 here in the middle, that is shared by both distribution switches. Now the clients will instead point to .3 as their default gateway, and so if the distribution switch that is operating as the primary goes down, well, the secondary can pick up and still use .3 to answer client requests to get off of their subnet. FHRPs are extremely important in network design, and we have three main FHRP options that we can choose from. First of all, we have the Hot Standby Router Protocol, or HSRP. Next, we have the Virtual Router Redundancy Protocol, or VRRP. And lastly, we have the Gateway Load Balancing Protocol, or GLBP. And we're going to be covering each one of these in more detail in the coming videos. So when it comes to network redundancy, it sure feels like it should be a simple conversation, right? I mean, just deploy more devices and deploy more connections. But it's more complicated than that. Here are the takeaways we need to keep in mind from this conversation. First of all, any chat around network redundancy should be centered around risk. The evaluation of that risk, keeping in mind we've got to think about things like what's the likelihood of that event happening and what's the impact if it does happen, as well as the cost of what it's going to take to mitigate that risk. And so all of that comes together and helps us make decisions around whether it makes sense to invest in more redundancy. And second of all, how we physically connect our networks together, that matters. We don't want to use squares, for example, in campus design. We want to use triangles connecting two distribution switches to an access layer switch as our primary example in that scenario. And lastly, it's not just the physical connections, it's also the configuration of those devices. In other words, the protocols that we're running. If it's a layer 2 environment, then we need spanning tree protocol and first hop redundancy protocols. And if it's layer 3, we're going to need another interior gateway protocol, or IGP, such as OSPF and EIGRP and all of those other options that we have available to us for running layer 3 down to the access layer. I hope this has been informative for you. I'd like to thank you for viewing. The Hot Standby Router Protocol, or HSRP, is Cisco's version of a first hop redundancy protocol, or FHRP. In this video, we're going to be exploring HSRP in more details, and that'll give us a better idea of how these FHRPs are designed to function. Let's dive in. The first thing to know about HSRP is that we have two different versions. We have HSRP version 1 and appropriately named HSRP version 2. Now, as we go through the different parameters that we're setting and the way HSRP functions, we will be identifying whether that applies to both versions or if it operates differently between the two. The other thing we need to know is that HSRP is configured in groups. When we apply two different groups to a router, for example, every default gateway that we configure is going to be part of a group. And so if we want our layer 3 devices to operate HSRP across different default gateways, well, then we are going to need different groups in order to make that happen. Now, when we configure HSRP and we configure a group, let's say we're running group 10 on both of these routers, and we assign the default gateway for group 10 to both of those routers, well, these routers are going to start sending hello messages to one another. At this point, there's going to be an election between these two routers to determine who should be the active, after which we will have one router in the active state, and the other router will be in the standby state. Now, HSRP only allows one router to be in the active state and one router to be in the standby state, but if, for example, we have a third or a fourth router on this network segment and is participating in the HSRP communications, then it's going to remain in what we call the listen state. All other routers that are on that network segment will be in the listen state, essentially listening in case one of the either active or standby routers fails. At that point, they can jump in and become part of the HSRP process if one of those two routers goes down. Now, this election happens on a per group basis, meaning that a router could be active for VLAN 10, but it could be in standby for VLAN 20. And our other router here, it could be the opposite. It could be active for VLAN 20. Load balancing active responsibilities among multiple routers is a very good thing. And we're going to be talking about that later on in this course when we cover FHRP design. So what does active and standby mean? When we think about FHRPs, we have to remember what we're trying to accomplish here. This client has a default gateway configured for, let's just say in this case, .1. Well, the idea here is that we don't want .1 to belong to the router on the left or the router on the right. we want .1 to be shared between the two, and that means we need different IP addresses for the layer 3 interface that's facing the client. In some cases, that'll be a physical interface. In other cases, it'll be a logical interface. But generally speaking, we call these the physical IP addresses. So let's say that these are going to be .2 and .3 on the respective routers. All right, so let's say this client is on VLAN 20. It's using .1 as its default gateway. And we look at how the election turned out, and we see that the router on the right is the active for VLAN 20. That means that when this client sends an ARP request, it's going to get a virtual MAC address back in response. And the router sending that response is the active, so the ARP response comes in from the active router. That virtual MAC address is going to be where I send my traffic from a default gateway perspective. That means that the rest of the switching environment is going to take my traffic and send it out to that active router. That active router will then send the traffic upstream, and then my packet proceeds out towards my destination as usual. Well, what if something happens to my router on the right? My active has just gone down. What is going to happen? Well, the standby router continues to listen for these hello messages that are being sent by the active router. And so it knows within a certain time frame that, hey, the active is down, time for me to step up. Which means I'm going to start receiving the traffic that is being sent to this same virtual MAC address. We call it a virtual MAC address because it can be shared by any device on the network. However, because MAC addresses need to be unique, it can only be owned by one device at a time. And specifically, that's going to be the active device, whether it's the one on the right or after a failure, the standby could step in and become the active router. Now, assuming this network segment here represents a switch of some kind, well, that switch already has that virtual MAC address listed going out to the router on the right. And it has no idea that that router went down and the router on the left now wants to receive traffic destined towards that virtual MAC address. So, how do we fix this problem? Well, what happens is the standby router sends a gratuitous ARP. That gratuitous ARP is essentially saying, hey, I know nobody asked, but here's an ARP response, and it gets broadcast out to the rest of the network. So every switched in the layer 2 domain is going to know where that virtual MAC address lives because we just sent a gratuitous ARP saying, hey, this is where that virtual MAC address now lives. It's going to replace the entry in the CAM table and say, okay, we're no longer connected to this interface. That MAC address now lives out this interface. So from the client's perspective, it continues to send to the same destination MAC address, which in our case is the virtual MAC address. So nothing has changed from the client's perspective. However, because of this gratuitous ARP mechanism, now the network has been updated to send it towards what was once the secondary HSRP peer, but is now the active. One of the goals of first hop redundancy protocols is that the client never needs to be reconfigured. It never needs to be changed based on what's happening upstream. Instead, the network converges and makes it so the client continues to operate as if nothing happened because it is completely unaware of what's happening upstream in the network, and that's what we want. So let's clean this up a little bit and come back to a couple of concepts. First of all, we have these hello messages. These hello messages are being sent out as multicast addresses onto the layer 2 domain. The reason we send multicast is so that we can be sure that it gets to the other routers on the segment, whether it's the other active or the standby, or even one of the listening routers that are part of that HSRP group. Now this MAC address is going to vary depending on whether we're using HSRP version 1 or version 2. And specifically, HSRP version 1 is going to use 224.0.0.2. That multicast address might look a little familiar because it has a different purpose. It is known as the all routers multicast address. By default, when we send a packet to 224.0.0.2, it's going to be received by all routers on that broadcast segment. That means that HSRP v1 does not use a unique multicast address for its communications. And that's not perfectly ideal. This is why with HSRP version 2, and let me go and give us a little more space here, HSRP version 2 is going to use 224.0.0.102. 102 is reserved for Cisco FHRPs. And yes, I said FHRPs, not HSRP. This is the same multicast address we're going to use for GLBP, which is another Cisco-made FHRP that we're going to be discussing in a couple of videos. But for now, we can think of this as a reserved multicast address for HSRP version 2. Now, when it comes to these hello messages, these are really important because not only do they establish communication, but it tells us when something goes down. So we're going to send these hello messages at a specific interval, and by default, that's going to be a 3-second hello timer. We also have another timer we call the hold timer, and that tells us that if we don't get a hello packet within this particular time frame, then we're going to assume that the other router is down. And by default, we set that to 10 seconds. Now, we can make these a whole lot faster because 10 seconds is a long time to wait for us to detect a failure. In fact, if we have HSRP version 2, HSRP version 2 allows us to go into the millisecond range. So we can get really fast with our hello timers, and hopefully that reduces any amount of downtime that we end up experiencing. Now that said, even better than using millisecond-based timers, we can use a protocol called bidirectional forwarding detection, or BFD. BFD was designed to be used in tandem with other protocols, such as HSRP, We're sending hello messages at a millisecond level. That can take a whole lot of CPU overhead. It can take a whole lot of network bandwidth even, just with the processing that's involved, relative to a very lightweight protocol like BFD, which can be sent more frequently with less CPU overhead. And so if BFD detects a failure, then it can alert the HSRP process, and HSRP will know that we've lost communication with the other router. We're going to be discussing BFD in more detail later on in this skill. Now, as we get deeper into network design, we're going to find that security is always going to be something that we need to consider. It should never take a backseat to other conversations. In fact, security should be the start of a lot of our conversations. So we should be asking, how can we lock down and secure HSRP? And the best way we can accomplish that is with authentication. We want to prevent accidental HSRP peerings, and worst case scenario, we want to prevent malicious HSRP peerings with somebody throwing a rogue router onto our network and trying to grab traffic that is supposed to be going to the active HSRP device. HSRP gives us two authentication methods. One would be plain text, and that's probably, as you can guess, not an ideal situation. We don't want to be sending our passwords in plain text. The other option would be MD5 authentication. So in nearly every case, we're going to leverage MD5 authentication to lock down our HSRP communications. So these routers are sending hello packets to one another on these multicast addresses, and this is when that election happens. So how do these routers decide which one is the active and which one is the standby? Well, the election is going to happen primarily based on a priority value. The priority value is going to be a configured value between 0 and 255, and 100 is the default setting if we don't change the priority level. And what matters here is that it's the higher priority that wins. So if we take one router and set it to 250, well, it will beat out all other routers that haven't had their priorities changed because their priorities are still configured for 100. Now, what if we don't change any priority values? What if they're all defaulting to 100 and there's a tie? Well, we break that tie by looking at the physical IP address, which again might belong to a logical layer 3 interface, whatever interface is pointing towards the subnet and pointing towards the client. And again, we are going to look at the highest IP address, where we had .2 on the left and .3 on the right. Well, the router on the right is going to win that tiebreaker because it has the higher physical IP address. And because we can't have duplicate IP addresses on a network segment, in theory, we are not going to have another tiebreaker after we look at the IP address. Now, even though our election is done and we've established who the active and standby routers are, we do have to take a step back and think about that scenario as far as what happens when our active goes down. Because if our active goes down, our standby goes into an active state. But guess what? Routers don't usually go down forever, and we should be thankful for that. So let's say now that router on the left has come back online, and we still have this router on the right in the active state. So the question is this: do we want that router to stay in the active state, or do we want the router on the left to resume its role as the active router? Well, in most cases, we want to keep a deterministic network, meaning we know what's going on at all times. And so we don't want the active just changing roles because a router rebooted somewhere. So in most cases, we're going to want that router to boot back up into the active state. But here's the problem. Once a router is in the active state, you can't just take it back over. We need to add a special configuration that we call preemption. Preemption is not configured by default. We must intentionally enable preemption if we want that as part of our HSRP design. So once we've configured preemption on the active router, if it goes down, comes back up, and really it should be in the standby state at that point, because we've enabled preemption, it's going to be able to tell the other router, hey, I am now the active router, and the standby router will return to the standby state. Now, for better or worse, we have one more piece of information that we're going to have to memorize in all of this, and that would be those virtual MAC addresses that we discussed earlier. Remember, when the client is sending information towards an HSRP managed default gateway, the destination MAC address will always be a virtual MAC address. And that virtual MAC address is determined by two things. First of all, the HSRP version 1 or version 2, and second of all, the group ID. So when it comes down to it, the virtual MAC address for HSRP version 1 is going to be 0000.0C07.AC and then XX. XX is going to be our group ID. And because MAC addresses are in hexadecimal, if we have two hexadecimal digits, so to speak, then we are going to have 16 by 16, which means we have 256 groups available to us. Now, HSRP version 2 has a different virtual MAC address. Its virtual MAC address is going to be 0000.0C9F and then simply .F with 3 X's after it. And hey, now we have an extra hex character, and so that means it's 16 times 16 times 16. Well, hey, that means that we have 4,096 groups in HSRP version 2. This is a big advantage between HSRP version 1 and HSRP version 2, and it's not because we are going to have 4,000 different VLANs that we want to run HSRP on in an environment. It's really more the fact that if I have VLAN 1000 in an HSRP version 1 environment, well, I'm going to have to choose a group ID that isn't 1000. Whereas with HSRP version 2, I don't need to worry about that. Doesn't matter what VLAN ID I have. If I have VLAN 2535, well, guess what? I can assign HSRP group 2535 as well. This isn't anything that's required from a HSRP configuration perspective. It's just something that helps us as humans identify something. When we look at group 2535, we can know that that belongs to VLAN 2535. It's nice to align those. But with HSRP version 1, we weren't able to do that. With VLAN 1000, for example, we might have had to have HSRP group 252, something that's just not quite as intuitive. So if your question is, do I have to memorize those virtual MAC addresses for the ENSLD? I would dare say yes. The virtual MAC address is definitely fair game for the ENSLD or any exam where HSRP is on the blueprint. And so I would take the time to memorize the virtual MAC addresses, not just for the exam, but also so that when we're working on the network and we see these virtual MAC addresses showing up in the CAM tables, that we know that those belong to HSRP. Okay, let's not sugarcoat this. There's a lot to take away from this HSRP conversation. Number one, we have two different versions of HSRP. So anytime we're thinking about HSRP, we need to think about the fact that, okay, there's version 1 and version 2. And in most cases, they operate the same way, but there are some key differences. Second of all, we are configuring those in groups. And we do recall that version 1 has 256 groups, version 2 has 4,096 groups. And it's one group per default gateway, by the way. Third, we are going to use hellos for communication. We're going to be sending those at specific intervals, and we can tune those timers or use BFD to help us improve failure detection. Fourth, we're going to use those hellos to establish communications and have an election. And the election is going to determine which router's in the active role, which router's in the standby role, and if we have additional routers, which ones are in the listening role. And the highest priority in IP address is going to win that election. Fifth, we have other options to consider, like authentication with MD5 hashing, as well as preemption. If we want the active router to come back online and resume its role as active, we need to configure preempt. And last but not least, we do need to memorize those virtual MAC addresses, so I highly recommend looking those over and just committing those to memory as best we can. I hope this has been informative for you, and I'd like to thank you for viewing. It's a tale as old as time. Cisco comes out with a really cool new protocol like HSRP, and the industry needs to follow suit with a standard that anybody can deploy, not just Cisco devices. In this video, we're going to be talking about the Virtual Router Redundancy Protocol, or VRRP, which is that industry standard version of a first-hop redundancy protocol. We're going to take a look at how VRRP functions, and especially compare it back to HSRP. Let's dive in. Now that we know how HSRP works, it's pretty easy to relate VRRP back to HSRP, just citing the differences between the two protocols. And the biggest difference between these protocols was already mentioned in the intro. VRRP is an industry standard protocol. Unlike HSRP, which is proprietary to Cisco devices, any networking vendor can deploy VRRP to their equipment. Something we have to consider as Cisco engineers is that if we have a Cisco router and we're connecting that to a router made by a different vendor, and we want to configure an FHRP between these two, well, VRRP is going to be our only choice. Because even though we can run HSRP and GLBP in our Cisco router, the other vendor isn't able to support those protocols because, again, they're Cisco proprietary. From there, we get into a few other differences. For example, we don't use the terms active and standby with VRRP. Instead, we use master and backup. Now, the way these roles are assigned is very similar to HSRP in that we're exchanging hello messages and we're performing an election. But one thing to keep in mind here is that even though we still use the concept of priority, in Cisco devices, when we're configuring HSRP, the priority level is going to be between 1 and 254. This should look a little different because in HSRP, we had 0 to 255. So we had all 8 bits of that range in order to configure as a priority. But with VRRP, 0 and 255 are reserved. And by the way, the default is still 100, at least on Cisco devices. Now, there is one huge difference between HSRP and VRRP that will affect our designs in some scenarios. And that specifically is that we can save IP addresses in VRRP. And this is tied to a concept in VRRP that allows us to use the master's physical IP address as our virtual IP. Here's how this works. In our scenario with HSRP, we assigned .2 and .3 to these routers, and we said we were going to share .1 as the default gateway. And we can still configure VRRP in the same way, where we have a virtual IP address that's different than the two physical IP addresses. However, we also have the option in VRRP where we can bypass this need to configure a virtual IP address, and we simply use, in our example, .2 as the virtual IP address. And when we configure it this way, it has some interesting ramifications. First of all, as we can see here, we save an IP address. We only need 2 IP addresses in this scenario rather than 3. Second of all, whichever router's IP address we choose to be the virtual IP address, that is by default going to become the master router. When we have a failure scenario and the master router goes down, the backup router is going to take on the .2 IP address, as well as the virtual MAC address, very similar to how HSRP functions. But the caveat is that we must have preemption enabled. In fact, it's just not even an option. We can't disable preemption because what's going to happen is when this master router comes back online, it's going to have that virtual IP address configured as its physical IP. So we can't have the backup router trying to be .2 and the master router trying to be .2. That's just not going to work. So in this scenario, when the master comes online, it will automatically preempt the backup router. Now earlier I said that this is very important for design elements, and you might be looking at this saying, okay, well that's great, Jeff, we saved one IP address out of like 256 on the segment. What's the big deal about saving one IP address? Well, we don't always use a first hop redundancy protocol for our clients. What if instead of a client down here, we have a router? What if this is a /29 subnet range that's been provided to us by a service provider, and we're connecting our master and backup routers to a service provider router? Well, in this case now, our /29 gives us 8 IP addresses, 2 of which we can't use, and so we actually only have 6 IPs on this segment. And so if we use HSRP, 3 of those must go to the HSRP process. And so we actually only end up with 3 that we can use, one of which has to go to the service provider router. So in the end, we only get 2. At this point, 1 IP address goes a long way because we can use 2 for VRRP, and that gives us 4 to use. And even though, again, it's only 1 IP address, that increases our usability by 33%. And that can be huge in a lot of scenarios. So clearly there are some scenarios where 1 IP address is going to help us out a lot, and that might entice us to use VRRP instead of HSRP. Now, a few other differences between VRRP and HSRP. Preemption is enabled by default. We recall in HSRP that we have to explicitly enable preemption if we want it to happen. With VRRP, it's configured by default. So if we want preemption to not occur, then we need to disable preemption on the master routers. And authentication, hey, this part is the same. We have open authentication and we have MD5 hashing. And as always, when it comes to security, we want the more secure solution, and so that would be MD5 authentication. So what about VRRP addressing? Well, VRRP does have a dedicated multicast address, and that would be 224.0.0.18. Furthermore, it has its own virtual MAC address, and its virtual MAC address is going to be 0000.5E00.01XX, where XX is the group ID. Now, when we think back to HSRP and how that worked, we understood that if we have 2 hex characters dedicated to the group ID, well, that means it's 16 by 16, so that's only 256 groups that we get with VRRP. So that would be a disadvantage to going with VRRP over HSRP version 2. Lastly, just like with HSRP, we have 2 versions of VRRP, and specifically that will be VRRP version 2 and VRRP version 3. Now, everything we've talked about up to this point applies the exact same to both versions of VRRP. And yes, that does include the virtual MAC address, which means that we have 256 groups regardless of VRRP version. However, version 3 does give us 2 key enhancements. First of all would be IPv6 support. VRRP version 3 is going to support IPv4 and IPv6, whereas VRRP v2 only supports IP version 4. And second of all, we recall that we talked about hello timers with HSRP and how we could use millisecond timers on HSRP version 2. Well, VRRP v3 is going to give us the same thing. It will allow us to tune our timers to use the millisecond range. So, as we've seen here, VRRP is very similar to HSRP. In fact, we just need to know the differences between them at this point. First of all, VRRP is an industry standard protocol, and from there, there's just a few other differences, such as we use master backup and preemption is enabled by default. Now, the key difference between these as far as design elements are concerned would be the fact that we can use the master's physical IP address as the virtual IP. Keeping in mind the caveats that go along with that, but hey, that can actually save us in IP address spacing. Third, the addressing is different. So from a multicast perspective, we have 224.0.0.18, and the virtual MAC address is different as well. Last but not least, we have VRRP version 2 and version 3. And with version 3, we not only get IPv6 support, but we can also tune timers at a millisecond level. I hope this has been informative for you. I'd like to thank you for viewing. You may have noticed as we reviewed HSRP and VRRP that both of these protocols leverage an active standby or a master backup type of topology, where the active and master, they're forwarding traffic, and the standby/backup router, they're just sitting there doing nothing. Now, we can't load balance that between VLANs, for example, by leveraging groups. However, what if we want both of those routers to forward traffic actively on a per group basis? Furthermore, what if we want to engage other routers? Remember, HSRP, we've got that listening state, and it's not doing anything. So if we've got 4 routers all sitting there, why not have them all forwarding traffic upstream? Well, that concept is why Cisco created the Gateway Load Balancing Protocol, or GLBP. In this video, we're going to explore GLBP and how it relates to HSRP and VRRP, but also how it enables that active-active forwarding that those 2 protocols are unable to provide. Let's dive in. Wow, look at this scenario. This client has it made. They've got their choice of up to 4 different gateways in the environment. But again, the key here is that we want to enable all of these at once. And that's exactly what GLBP is going to allow us to do. The first thing we need to understand about GLBP, by the way, is that it is another Cisco proprietary protocol. So unlike VRRP, we're only going to be able to use this on Cisco devices, which means that all 4 of these routers in our scenario must be Cisco. And again, the goal of GLBP is to do active-active load balancing across multiple gateways. Or potentially, in our case, active-active-active-active. And specifically, we can support up to 4 different gateways in the environment. The way we're going to start this is the same way we begin with HSRP and VRRP. We are going to perform an election. And the way we perform that election is by leveraging priority. And yes, the higher priority wins, just like before. And we're going to use the IP address as the tiebreaker. The difference is that we are no longer electing who's going to forward the traffic. We are simply electing the active virtual gateway, or AVG. In our scenario, let's say that the router on the left becomes the AVG. The AVG is then going to assign a different role called the active virtual forwarder, AVF. And this is what we can have up to 4 of. So in our scenario here, we'll assign AVF roles to the other 3 routers. And yes, the active virtual gateway can also assign itself as an active virtual forwarder. So that can be our 4th AVF. Now, just like with the other FHRPs, we are going to have a virtual IP address that's configured as the default gateway. So this client down here has its default gateway configured to be that virtual IP. So how exactly do we go about load balancing this traffic? Well, the key here is that we are going to use different virtual MAC addresses per active virtual forwarder. So we'll have VMAC1 here on the left, we'll have VMAC2 here in the middle, and so on and so forth. Next, when this client decides that it wants to send traffic off of its subnet, it's going to do what clients do, and it's going to send an ARP request. Now that ARP request will be received by all 4 of these gateways. However, the active virtual gateway itself, the AVG, is going to be the device that responds. So specifically, it's going to send the ARP response back, and as part of this ARP response, we are going to choose one of those virtual MAC addresses. So it's going to choose virtual MAC address, and we'll just say X. We don't know. Virtual MAC address 1, 2, 3, 4. Whichever virtual MAC we choose is what the client is going to record in its ARP table. At that point, thanks to layer 2 communications, when we send our next packet from that client, it's going to land on whichever AVF was chosen by the AVG. So a natural question to ask at this point would be, how does the AVG choose which virtual MAC address to provide? And we actually have a say in that when we're doing the configuration of GLBP. And specifically, we have 3 different load balancing methods that we can choose from. The first of which is the default, is round robin. Round robin means that we are simply going to take turns. So the first client who shows up is going to get VMAC1, the second client will get VMAC2, and so on and so forth. The second method would be weighted. What if in this scenario I had different bandwidths on my upstream connections? What if the router on the left has a 20 meg circuit to the network and the other routers have 10 meg circuits? Well, in this scenario, I would want the router on the left to receive twice as much traffic so I can consume that bandwidth at a more appropriate rate. So similar to how I configure priority on a per router basis, I can configure a weight. And so I can configure my weight on this router to be 20 and the weight on the other routers would be 10. At this point, my AVG will hand out virtual MAC addresses at the appropriate rate based on my weighted configurations. Now, the third methodology is something we call host dependent. The goal of host dependent is to always make sure the client receives the same virtual MAC address. So if it shows up one day and it's given a VMAC of 1, then when it comes back the next day, it needs to also be given VMAC 1. The way we're going to do that is we're going to check out the MAC address of that client when it registers, and we're going to base our VMAC response on that MAC. So we as network engineers get to decide this, and in most cases, we're probably going to go with one of the first 2 methods. But if, for example, we have a highly mobile network and we want a consistent experience across all of our clients, then we might want to consider host dependent as our load balancing method of choice. Now, no FHRP discussion is complete without talking about failure scenarios. First of all, let's consider what happens if the AVG goes down. If we lose our AVG, we are going to perform another election based on the priority and the IP addresses of the other routers. One interesting thing to note here is that we don't actually have a backup AVG on standby at any given moment in time. We truly have to perform another election when we detect that the AVG has gone down. Now, what if we lose an AVF? What happens if, say, AVF2 goes down, so we've lost virtual MAC address 2? Well, our AVG is going to detect the failure of AVF2, and it's going to assign AVF2 virtual MAC addresses to one of the AVFs. And yes, it is a candidate for that as well. Now, let's say it chooses AVF3 for that, and in that scenario, AVF3 is going to receive an unfair amount of traffic, so to speak, because it's also answering now for VMAC2. So it has 2 virtual MAC addresses, whereas AVF1 and AVF4, those are still processing only 1 MAC address. So ideally, router number 2 comes back online and it can take its virtual MAC address back. However, in the meantime, AVG is not going to be handing out VMAC2 to the ARP requests that come in. So even if router 2 doesn't come back online, the traffic will eventually reload balance itself. So just to close out the GLBP conversation, we do still use timers. We've got the hello and the hold timer. We also have authentication, same thing. We've got open and MD5 authentication. The multicast address we mentioned in the HSRP conversation, but it's going to be the same thing as HSRP version 2, which is 224.0.0.102. Cisco reasons that you're not going to be running HSRP and GLBP at the same time, and so, hey, why not use the same MAC address for them? And incidentally, by the way, even if we do have HSRP and GLBP running on the same broadcast domain, it's not going to be a problem. They're just going to receive each other's traffic and then drop it because, hey, I don't actually need this. And you were probably hoping I'd forget about this, but we are going to cover the virtual MAC address for GLBP. And the virtual MAC address in this case is going to be 0007.B40. And here's what's interesting at this point. We're going to put an X here, and then a dot, and then XXYY. Now, XXX is representative of the group ID, just like with HSRP and VRRP. However, what we can't really tell by looking at this is that GLBP only gives us 10 of those bits. We don't actually get all 12 of the bits that would normally be afforded to us by 3 hex characters. And as a result, we only actually get 1,024 different groups in GLBP. I do not know why they configured it that way, but we do need to be aware of this. Now, the YY is new. We didn't have YY in HSRP or VRRP, and YY is going to be the AVF ID that is assigned by the AVG. Remember, we need different virtual MAC addresses for all 4 of these routers in our scenario. And so something has to be different, and yes, it's the YY at the end of the virtual MAC address that's going to differ among our different AVFs. So as we've seen, GLBP does operate quite a bit differently from the other first hop redundancy protocols, but let's not be intimidated by that. Instead, let's make sure we understand all the different ways GLBP functions. First of all, we need to know that GLBP, it load balances, right? That's the whole point of the protocol. And the way it does that is with electing an active virtual gateway, that would be an AVG, and up to 4 different AVFs, active virtual forwarders. Second of all, we have 3 different balancing methods that we can configure. The first one would be round robin. Second would be weighted. Third would be host dependent, so make sure we understand the differences among those. Third, we have to consider the different failure scenarios. If an AVG goes down, we have a new election. If an AVF goes down, we have a VMAC reassignment. And last but not least, we need to remember the addressing. So multicast address is 224.0.0.102. It's the same as HSRP version 2. And then we have the different virtual MAC address for GLBP that not only takes the group ID into account, and again, only 10 of those bits, but also the AVF ID. I hope this has been informative for you. I'd like to thank you for viewing. If we're going to configure high availability in our campus networks, we better get used to the idea that the default timers that are on our routing protocols and first hop redundancy protocols, that these timers are way too slow. And our initial reaction might be, oh, okay, well, we'll tune those timers. We talked about how HSRP v2, for example, has millisecond timers. That sounds a whole lot better than waiting seconds to detect an HSRP failure. And that is true. But we have a little bit more sophisticated of a method for detecting when there's a failure. In this video, we're going to explore what that sophisticated method is, and it's bidirectional forwarding detection, or BFD. Let's dive in. Here's the scenario. Let's say we have 2 routers that are directly connected in some fashion, whether that's Ethernet cable or serial line, and we are running a routing protocol between the 2. Let's call it EIGRP. Now what happens if the router on the right goes down for some reason? What would happen from an EIGRP perspective? Well, fortunately, Cisco has built some intelligence into these routers such that they will detect that there's an electrical failure out this line. Because this link right here is actually in a physically down state, we can assume that the neighbor on the other end is no longer reachable. And so we are going to instantaneously recognize the failure. And that's great, but let's consider a different scenario. Now let's assume those routers are connected to each other via a switch. Now the router on the right goes down, and so this link is going to go down. The switch will detect that as an outage, but this router on the left, it doesn't see the outage. Because it detects the electrical connection between itself and the switch, it knows that that link is still up, and therefore it has no idea that that router went down. This is when we rely on the timers in our routing protocols. We are sending hello messages back and forth to each other, and if at some point the router on the right stops sending hello messages, even though we continue to send them ourselves, well, eventually we're going to say, hey, you know what? I think that router is down. I haven't received a hello message in a specific amount of time. And so I'm going to decide that that has gone down, but look how much time has passed in the meantime. In fact, by default, a lot of our timers are not great for this. EIGRP, for example, is going to wait 15 seconds before deciding that its neighbor is down. And OSPF is even more, it's 40 seconds. Now, fortunately, a lot of these routing protocols do allow us to tune the timers, but let me paint an example for you of what that looks like. Let's say that you and I are playing a game of catch. We're throwing a ball back and forth, except in this case, the ball that we're throwing back and forth is a bowling ball. Which, as I say, that doesn't seem like a particularly great idea, but hey, you know, we're throwing this ball back and forth, and if we're not too far apart from each other, we're probably able to toss the ball back and forth to each other every, 10, 15 seconds or so? Because the ball is heavy, and so we've got to take the time to catch it properly and then toss it back at you so it doesn't hurt you. But imagine somebody then tells us that we have to toss this ball back and forth every single second. Can you imagine what that's going to look like? Because that ball is heavy. And it's hard to handle, and so if we're trying to go that fast, eventually one of us is going to drop that ball on our foot, and we're going to end up going to the hospital instead of playing catch. The reason I bring this up is because when we're using the hello timers from our protocols, we are processing actual control plane traffic with every hello message we send. And these control plane messages, they are weighty. They're like bowling balls. When routers are sending hello messages back and forth to each other every 5 or 10 seconds, well, that's easy to handle because, it's just like us tossing a bowling ball back and forth. We can probably do it every 5 or 10 seconds safely. But as soon as we try to crank that up and say, you know what, we're going to send this back and forth at 1 second intervals. And in some cases, we can actually make it millisecond intervals. What we're doing is we're asking those routers to send very weighty messages to one another. And when I say weighty, what I really mean is this results in CPU processing. Because the route processors themselves have to receive those control plane messages and process them. So yes, we can tune these timers and send hello messages at a greater frequency, and on the surface that appears to solve our problems, but it might actually cause us greater problems from a CPU processing perspective. This is where BFD comes into play. BFD is a low overhead protocol. Where we used bowling balls as our analogy before, these are more like ping pong balls. Think about tossing a ping pong ball back and forth. We can probably do that pretty fast and pretty safely. BFD is not a routing protocol in itself, but rather it works with other protocols. And the best example of other protocols that it works with would be routing protocols like EIGRP and OSPF, and first-step redundancy protocols like the ones we've been discussing, HSRP and VRRP. Though I should note that it does not integrate with GLBP, because with GLBP, we're less interested in detecting fast failures because we have all of our routers active at the same time. Even better, when it comes to timers, we can get BFD down to 50 milliseconds. There's not a whole lot of routing protocols out there that can match the frequency at which we're sending messages to one another using BFD. So let's say we have configured HSRP in this environment, and HSRP is going to send hello messages back and forth. And we want to improve how fast we detect HSRP failures. Well, rather than tuning the HSRP timers, let's leave the timers alone on HSRP. Instead, let's configure BFD and integrate BFD into the HSRP process. Here's how this works. We are going to be sending HSRP hello messages to each other every 3 seconds, which is the default. In the meantime, BFD is going to be sending messages back and forth to each other every 50 milliseconds. I can't even draw these at the appropriate scale with how many BFD messages are going to be sent in between the hello messages. If we have our failure scenario where the router on the right experiences an outage on its link, well, that's going to happen sometime in this process. Let's say it happens right here in between the hello messages. Well, normally we'd have to wait not only for the first hello message to be missed, but then 2 more hello messages would have to be missed before we finally decided, all right, you know what, we're going to go ahead and assume that that HSRP active router has gone down. Instead now, we wait for 3 BFD intervals, which at 50 milliseconds, that'd be 150 milliseconds. BFD then realizes after 150 milliseconds that that HSRP peer has gone down. And it's going to alert HSRP to say, hey, that's down, and enable the standby router to take over as the active. Now, one secret to BFD's success is this concept called echo mode. In a lot of cases, echo mode will be enabled by default, but we have to check the platform specifics to make sure of this. The reality with BFD is that we have a similar situation to what we just described with all of these other hello timers, where we have to send a packet to the other router, and then that router has to sit there and process it and realize, okay, hey, I just realized that I received a BFD message. Well, even though it's low CPU overhead, if it has to sit here and process it, well, that could introduce a lot of jitter and delay with responding to BFD messages. So instead, we use echo mode. What echo mode does is when we send a BFD message to the other router, it doesn't process it. It simply echoes it back to the sending router. This is an asynchronous operation, meaning that I don't actually need the other router to process anything. I am sending the message out, and if the router is alive on the other end, I'm going to get that message back. And so if I enable this on both sides, what I'm going to end up getting is 2 separate asynchronous operations that essentially makes this two-way communications. And in a way, we just BFD'd ourselves, because what we're doing is we're going to continue to send the control plane messages of BFD back and forth to each other. And this is going to happen at slow timer intervals. So there's a concept in BFD called slow timer. And when we talk about slow timer, well, that sounds bad, doesn't it? I mean, BFD and slow timers, those are 2 aren't supposed to mix. But the slow timer concept says that I'm really going to send my control plane messages at longer intervals, potentially up to 1 second in length. And the reason I can back down on my control plane messages is because echo mode is handling the failure detection. So if your mind is still focused on this concept of playing catch with a bowling ball, then let me review what we've covered so far. First of all, indirect failures rely on timers. We understand if two routers are directly connected to each other, then we're going to detect failures pretty fast if a link goes down. But in a lot of cases, especially with HSRP and other first hop redundancy protocols, routers aren't going to be directly connected to each other. There's not a whole lot of purpose in configuring an FHRP on a direct link. And so those indirect link failures are where we need a little bit of help. Now, second of all, those timers for the routing protocols and the FHRPs, they can be tuned, but they have a lot of overhead. The CPU has to process all of that, and again, that's where the catching or playing catch with a bowling ball analogy comes into play. And we definitely don't want to ask our routers to do that. As such, this is where bidirectional forwarding detection comes in. BFD is a low overhead protocol and can be tuned all the way down to 50 milliseconds. And keep in mind, though, that we want to make sure echo mode is enabled. In most cases, it will be enabled by default, but it's something to check. And echo mode is going to further reduce any uncertainty in processing that's going to happen on the CPU side. When I say uncertainty, I guess I mean jitter and delay and such that's caused by the CPU processing on the other side. I hope this has been informative for you. I'd like to thank you for viewing. Have you ever found yourself in the candy aisle at a store trying to make your decision about which candy to pick and they just all look so delicious you can't make up your mind? Well, we might find ourselves in the same situation with our first hop redundancy protocols because we've looked at some great ones. We've got HSRP and VRRP and GLBP. And how do we decide among all three of these? And then once we do make the decision, how exactly should we deploy that into our network so that it's optimized and tuned? And I mean, this is a design course, right? So at some point, we do need to take a look at how we should build out our network architecture. Well, in this video, we're going to talk through the decision-making points that we want to consider when choosing an FHRP, and again, how exactly we would deploy that into our network. Let's dive in. When most network engineers first learn about these first hop redundancy protocols, and they're reading about GLBP and all of the features that it has, the inclination is usually to believe that GLBP is simply the superior protocol and we should always deploy GLBP. But the reality is that in the vast majority of networks, we're not running GLBP. We're either running VRRP or HSRP. And we'll get into the reason as to why. But when it comes to GLBP itself, the primary benefit to GLBP is right there in the name. It's the fact that we can load balance traffic. And furthermore, we can load balance traffic on up to 4 different gateways. Now, the reality is that in most cases, we're never going to have 4 gateways on a network segment. Generally speaking, we're only going to have 2 gateways on a network segment. And when you look at VRRP and HSRP and the fact that we can leverage multiple groups across multiple VLANs, which we'll cover here in a little bit, we can actually load balance across 2 different gateways with these 2 different protocols. So GLBP immediately loses a lot of its value when we only have 2 active forwarders on the subnet. Couple that with the fact that it's a complex protocol relative to VRRP and HSRP. I mean, most network engineers out there do not fully understand GLBP, which makes maintenance and troubleshooting a bigger issue. So when we take that into account, yeah, we get why GLBP isn't used very often out in the real world. But it is still good to have as an option. So if we're not deploying GLBP, well, maybe we want to deploy VRRP, right? I mean, VRRP is an industry standard protocol. It can run on anything, which might future-proof us, right? Because if we end up replacing one of our 2 routers with a non-Cisco router, well, it'd be nice to have VRRP in place in order to just pick up right where we left off and keep going. Furthermore, VRRP gives us that concept of saving an IP address. We can do that by setting the master's physical address as a virtual IP, which we covered in the VRRP video. And those are 2 very good reasons to go with VRRP. In fact, one could argue that there's not a whole lot of reason to go with HSRP over VRRP or GLBP. And yet, we see the vast majority of Cisco networks deployed on HSRP. Why is that? Why would we deploy HSRP when VRRP and GLBP have features that HSRP doesn't have? And the primary reason for this is simplicity. It's the same reason why most Cisco networks deploy rapid per VLAN spanning tree when the industry standard multi-instance spanning tree is superior in most ways. But the reality is that we have a comfort level with HSRP in the same way that we have a comfort level with turning on rapid per VLAN spanning tree. It all just sort of works. We feel confident in our ability to run HSRP commands and troubleshooting commands. So ultimately, when evaluating which protocol to use, the vast majority of organizations are going to look at this and say, first of all, do I need multiple active gateways? If I don't, then GLBP is probably not for us. Second of all, are we a Cisco shop? Because if we're a Cisco shop, we're not going to worry about deploying a non-Cisco router into the mix. And then it really comes down to, do we need that IP address? If this isn't a /29 or /28, then one IP address is not going to make a big difference. And so if I need neither of those VRRP features, I'm probably going to say no to VRRP as well. And so HSRP ends up winning by default simply because it's the protocol we're most comfortable with. Now here's a question for you. Is this a valid reason to deploy a protocol? Should we really consider deploying what might be perceived as an inferior protocol simply because our network technicians are more comfortable with it? And the answer is a resounding yes. We should absolutely take our comfort level with a protocol into account when we're doing our network designs. Remember, we need our network designs to be maintainable. We need our network designs to be able to be troubleshot. If we can't work on our network with ease, then it's going to make it a much more difficult environment to maintain over the course of time. But sometimes it's hard to accept this from a technical perspective because we look at, again, the features of GLBP and VRRP and say, well, those are superior. We should deploy those. And on paper, that sounds great. But in reality, sometimes it makes sense to stick with the protocol that we all know and love. Ultimately, what we have to do is we have to weigh these two choices. We have features on one side and we have simplicity on the other side. And what we need to do is weigh the two different options on a scale, so to speak, and say, okay, does it make sense to give up these features for simplicity? Because in some cases, hey, we need those features, whether it's an FHRP feature set or the feature set of a different set of protocols that you're considering. And so unfortunately, in those cases, we're going to have to go with a more complex, more unfamiliar technology, and that's fine in a lot of cases. But at the same time, we can't give zero weight to simplicity and comfort because those actually should weigh into the decision. Now, I just mentioned that we could load balance across VRRP and HSRP. What do I mean by that? When we have a pair of layer 3 devices, whether those are routers or multi-layer switches, and we have multiple subnets attached to the same set of routers, and I'll designate those subnets with different colors here, what we can do is make these routers active and standby for the two different VLANs. So for example, we can make them active and standby for the yellow subnet, but for the pink subnet, we flip those roles. We make the router on the right be active and the router on the left be in standby mode. Now this is admittedly limited load balancing because it's load balancing per subnet, and if the yellow subnet, for example, is 3 times as busy as the pink subnet, then yes, the router on the left will be getting 3 times the traffic that the router on the right is getting. But generally speaking, the more VLANs we have, for example, if we have 20 VLANs that we're splitting between these two routers, well, it usually ends up balancing out in the end. Now, one other thing we need to consider is that if these are multi-layer switches, let's call them layer 3 switches, then we want to make sure that we align the active, or with VRRP, for example, the master, we'd want to align that with the spanning tree root. And there's a very specific reason for that. Because in those situations where we have 2 layer 3 switches and they're connected to each other and we're sending these down to an access layer switch, for example, imagine a scenario where we have the HSRP active as an SVI on the switch on the left, but the spanning tree root is the switch on the right. What should happen here is that the link on the left is going to go into a blocking state. And this means that all traffic has to traverse up towards the root. That's exactly what we want in a spanning tree environment. But where's this traffic going? If this is traffic that's destined for another subnet, which, hey, most of our traffic is destined for other subnets in a network, well then all of that traffic is going to have to hit the root switch and then go across the interswitch link to get to the HSRP active. This is an inefficient design, and this is why we should always align the two. Because if instead the active is on the right and the standby is on the left, so the left is no longer the active, well hey, now our communications can go straight up and down between the active node and the access layer switch. Incidentally, by the way, if this is a data center environment, we're running virtual port channels, which isn't within the scope of this course, but at the same time, again, just broadening our horizons here. If we're deploying virtual port channels on these switches, then we would want to make sure that the VPC primary is also on the same switch. So ideally, we'd have the VPC primary with the HSRP active with the STP root role. That would be a data center conversation, but hey, we need to deploy FHRPs into our data center as well, so keep that in mind. Now next, we should absolutely consider using bidirectional forwarding detection with our FHRP. In fact, there's really no reason not to use BFD with most of our protocols, first hop redundancy protocols or interior gateway protocols. So we'd absolutely want to use BFD regardless of which protocol we're deploying. Now, as I mentioned in the last video, GLBP doesn't actually support BFD, and the reason for that is because if the active goes down, the other routers continue to forward anyways, and so we aren't quite as concerned with fast failover in that scenario. But if we're deploying VRRP or HSRP, we should absolutely deploy BFD rather than tuning timers. Now there is one more optimization technique we should consider, and we have not covered it yet in this skill, and that is a concept called object tracking. Object tracking is very similar to BFD in the fact that it's going to run independently of any protocol, and so it's kind of doing its thing, and then we can tie this into other protocols like HSRP and VRRP and such. And specifically what we're going to do is we're going to track things such as route reachability and IPSLAs and line protocols. We're essentially going to be tracking what's going on in the network, and if something bad is happening in the network, we might want to change which of our routers is the active router. So here's a great example. I know this is getting a little busy here. So if we have a third router upstream, and we have connections between these two routers up to that router, And we're on the pink subnet, so active router is on the right. Well, what happens if this link goes down? By default, this router continues to be the active router, which means that traffic coming on the pink VLAN is going to hit this router, and the router is going to check its routing table, realize I don't actually have a route upstream anymore, so I'm going to go through my neighbor across the pink subnet still and send it over to the other router. Well, at that point, it'd be a whole lot more efficient if the router on the right would simply stop being the active router, defer to the other router to allow it to be the active, and then clients can simply send their traffic up through the active router on the left. That's what object tracking allows us to do. We can track this interface state, and if it has any problems at all, we can lower the priority of a first hop redundancy protocol. And this is the key point. We're going to lower the priority via object tracking if the network is in an impaired state. So let's say that link goes down and we lower our priority by 50. So let's say we go from 120 down to 70. That would be an example here. And so the router on the left is still sitting at priority level of 100, and now 70 is less than 100. But we're not done, because here's a quick mental exercise. If the router on the right is 70 and the router on the left is 100, will the router on the left automatically take over in that scenario? And the answer is, well, that depends. It depends on a key configuration, which is preemption. Preemption must be enabled in order to take advantage of object tracking, because we can affect the priority all we want, but if the router is already in an active state, then the other router is going to need preemption enabled in order to take over. But as we can see here, object tracking is a way for us to maximize the efficiency of our traffic in the event of network impairment. All right, so if you were hoping I was going to sit here and tell you exactly which FHRPs to deploy, you're probably a little disappointed. Because the reality is, when we're making our decision, we need to take all kinds of things into account. And that's just really the primary takeaway here, is we need to look at our network, look at the pros and cons of all of these FHRPs, and make our decision from there. Now, when we're deploying these, keep in mind, if we're deploying HSRP and VRRP, then we can still take advantage of load balancing across the two routers, even though one of them's in a standby or backup state. And the way we do that is by taking advantage of groups. And so we'll make one router the active for one group and one subnet, and then we'll make the other router the active for the other group on the other subnet. Now, we can also make sure that we're maximizing the efficiency of our traffic by aligning the HSRP active or the VRRP master with the STP root if we're doing this on layer 3 switches. So that's going to make it so that, again, that scenario that we looked at on the whiteboard here, that as traffic is coming into the access layer switch, that's not getting sent up to the wrong switch and then over to the active. Well, let's make sure it only has to go across one hop in order to get to the active gateway. Last but not least, from an efficiency perspective, we absolutely want to leverage BFD and object tracking. BFD is going to help us with our timers and detecting failures faster, and then object tracking is going to help us with network impairment and making decisions based on that. I hope this has been informative for you, and I'd like to thank you for viewing. The ENSLD blueprint calls out graceful restart as something that we need to know while studying for this exam. But graceful restart is really just part of this overall SSO and NSF process that Cisco supports in its routing and switching platforms. In this video, we're going to take a look at what exactly stateful switchover and nonstop forwarding, or SSO and NSF, are, and how graceful restart ties into that. Let's dive in. A lot of this conversation is going to come down to control plane operations. When we have two devices communicating with one another, we like to just draw these router icons and switch icons and draw lines in between them indicating they're connected to each other. But really, when we break it down, here's what's happening. We have control planes and data planes on each one of these devices. And the control plane is communicating with each other and using a protocol, something like, let's say, OSPF, for example. So let's say we're running OSPF for exchanging routes between these devices, and OSPF is populating a database that is stored at the control plane. Now, we use that database to populate information in the data plane. Specifically, when it comes to routes, we're going to populate that routing table. That routing table is known as the routing information base, or RIB, and we're going to take the RIB and populate the forwarding information base, or the FIB, to leverage Cisco Express Forwarding, or CEF. But that's a conversation for another day. That's just what's happening under the hood. Ultimately, what we want to accomplish with this conversation is to stabilize the operations that are happening between these two devices. And specifically, this is going to come back to an architectural level conversation with some of Cisco's platforms. For example, Cisco makes chassis switches, and when we think about classic chassis switches, we think about the 4500s and the 6500s, but more modern chassis switches would be the 9400s and the 9600s. But either way, these chassis support dual supervisors, these supervisor line cards, and the supervisors are managing the control plane. Then we also have certain router platforms that essentially have the same operation, except instead of supervisors, they're running what we call route processors. Now really in any layer 3 device, the route processor is going to be responsible for all of the control plane operations. And when we talk about supervisors, really there's a route processor on the supervisor that's handling that control plane information. So it's just a matter of terminology between these two different architectures. So the question is this: when we lose one of these route processors, we want to fail over to the redundant route processor, well, what does that process look like? It's easy to take for granted that this operation is just going to happen magically, potentially, but that's not how it works, right? We need to understand the technology under the hood that's going to make it so we can move from one piece of hardware to another. If we look at the situation here, if we're going to lose our control plane, two things are going to happen. One, this relationship is going to go down. We're going to lose OSPF peers. Second of all, we're going to lose this ability to populate the data plane. So even if we have a modular device like a chassis switch, and we still got all of our line cards, and we want that communication to still happen between the two switches, well, that's going to be problematic because our data plane has lost all of the control plane information. And our two technologies that are going to help us with this are going to be stateful switchover, SSO, to help us keep that data plane online, and the nonstop forwarding, or NSF, is going to help us stabilize the routing relationship. First of all, let's look at stateful switchover, SSO. The goal of SSO is to make it so we can fail over from route processor to route processor as seamlessly as possible, all the while keeping data plane functionality online through this process. And the way we're going to accomplish this is by copying all of our control plane information live to the backup route processor. This means that if we have an OSPF database on this side, then we're going to have a fully populated OSPF database on the redundant route processor. Now, in order to accomplish this, this route processor is going to have to be in a powered up state, which is all right because the last thing we want to do if our primary route processor goes down is to have to boot up the second route processor. That's going to add a significant amount of time to our recovery process. The other thing we need to accomplish in all this is to keep that data plane online. So when it comes to that routing information base, in other words, the routing table, we do not want to flush this just because we've lost our control plane. Instead, we're going to keep this up until the route processor transition has completed. But that's it. SSO is all about keeping that redundant route processor in an active state, ready to take over on a moment's notice. The goal here is to get this transition completed within seconds of the route processor going down. Now, the temptation might be to look at this and say, oh, okay, well, SSO is so great and we're up within seconds. Why do we even need nonstop forwarding? But we do still have that same problem, because while we are transitioning from route processor to route processor, we're not sending OSPF hellos. We're not sending BFD packets, for example. And so in many situations, we're going to drop this OSPF neighbor because we're no longer responding. Yeah, if we're using default timer, seconds sounds great, but again, think back to BFD and the fact that we can detect a failure in 150 milliseconds. Now, this could be a big problem for us still, and we want to keep this OSPF relationship alive during the route processor transition. So let's talk about nonstop forwarding, or NSF. NSF is going to rely on our routers when they first form a routing relationship between each other, whether that's OSPF or EIGRP or whatever protocol, as long as it supports NSF, we want to advertise to one another our NSF capabilities. NSF absolutely requires that both sides not only be capable of running NSF, but also be enabled to run NSF. So now let's say the router on the left loses its route processor and it's going through this transition using stateful switchover. In the meantime, the router on the left has detected that its neighbor is down. But because we've enabled nonstop forwarding, we are going to simply mark all of the routes that we've learned from that router as stale. We are not going to pull those routes from our routing table. Instead, we're going to continue to forward that traffic at the data plane. Now, when this peer comes back online and now our backup route processor is fully functional, it's going to send a graceful restart message to its neighbors. It's essentially saying, what did I miss? Because I've been out for a long time, right? I mean, from a router's perspective, seconds is a long time. And so it needs to be updated on anything it might have missed. Because, hey, in the meantime, this router over here is still exchanging routes and learning things from the rest of the network. So it's going to respond with all the information, and that router will update its routing table as needed. So generally speaking, when we're talking about graceful restart, we're really referring to nonstop forwarding. A lot of Cisco documentation will use these phrases interchangeably, but graceful restart can leverage other mechanisms besides NSF. But in most Cisco architectures, SSO and NSF are going to be how we, again, come back to this concept of stabilizing the network when we experience outages of components on these modular systems. So hopefully that demystifies what's happening under the hood when we talk about these route processor or supervisor failovers. So when it comes to SSO and NSF, these technologies are for those devices that have redundant supervisor, redundant route processors. It's for failing over from one control plane to a redundant backup control plane instance. So when we talk about SSO, stateful switchover, the goal of SSO is to keep the data plane online and to fail over as quickly as possible from one control plane element to another. So that's, again, that actively copying tables back and forth and keeping the redundant hardware in an online state. Lastly, nonstop forwarding is to keep the external control plane relationships alive, because even though we could fail over super fast locally, in the meantime, all of our neighbors are going to think we're down, and that's going to cause ripple effects through the network, and that would be bad. So NSF helps maintain those relationships and overall helps stabilize our network. I hope this has been informative for you. I'd like to thank you for viewing. It's always best to review what we've learned at the end of a skill, and what better way to do that than by taking a quiz. First up, out of 5 questions, what are the authentication options available for HSRP, VRRP, and GLBP? And by the way, be sure to pause this video if you need more time to answer any of these questions. Well, technically speaking, there are 3 options. The first of which would be no authentication. It's not the best option, and we wouldn't recommend it. But another one that we probably wouldn't recommend is known as plain text. Plain text authentication will be sending that password in plain text, meaning anybody can listen in if they're sniffing the network traffic. So that's not particularly ideal either. Lastly, we have MD5 authentication. This authentication method uses the MD5 hash to scramble that password, which makes sure that nobody can listen to the network traffic and decipher what that password is. All 3 of these methods are available for all 3 of the FHRPs that we discussed. Next up, match the following FHRP properties to either HSRP or VRRP. Well, let's go through each one of these and identify whether it belongs to HSRP or VRRP. First of all is the master and backup roles. Those belong to VRRP. HSRP uses active and standby, which actually is down here in our list as well. So we'll just go ahead and mark this as HSRP letter E. Back up at the top here, we have 224.0.0.18 as our multicast address. Well, that's also VRRP. Cisco with HSRP, they used 224.0.0.2 for HSRP version 1, and then they used .102 for HSRP version 2 and GLBP. Next, supporting 4096 groups, well, that would be HSRP, and specifically HSRP version 2. Version 1 supported 256 groups, and that's what VRRP supports as well. Next up, sharing a virtual IP address with the physical IP of a router, well, that would be VRRP. HSRP is not able to do this. In fact, it requires a dedicated virtual IP address. Lastly, at the bottom there, preemption being disabled by default, that would be HSRP. VRRP comes with preemption enabled by default, and HSRP comes with it disabled by default. Question number 3. How does GLBP load balance traffic across multiple active gateways? This is an open-ended question, so be sure to think through the process of how exactly this occurs. When we have multiple active gateways, we have to make sure that we're able to take the client traffic and load balance it across all of them however we choose. Again, remembering that GLBP has 3 different load balancing methodologies. But specifically in this question, what we're concerned with is how exactly are we splitting that traffic up? And the way we do that is with ARP. When a new client comes online and submits an ARP request, the Active Virtual Gateway, or AVG, is going to respond to that ARP request with one of the virtual MAC addresses that belongs to all of the active virtual forwarders, or AVFs. So as more clients come online and continue to send ARP requests, the AVG will respond to those ARP requests with different VMACs from the different AVFs, and thereby load balancing our traffic across all of these different gateways. Next up is a true or false statement. When BFD is enabled, the protocol timer should still be tuned to minimize failover time. Well, the answer here is false. Remember, one of the purposes of BFD is to offload sending those huge packets. Remember the bowling ball analogy. Sending protocol-based hello timers like OSPF or EIGRP and such. These hello timers take a lot of CPU processing. We want to leave these timers alone when we're configuring BFD, because BFD is going to handle the failure detection for us. And we've come to our last question. Identify the redundancy mechanism belonging to each of these functions. Well, let's just go through these one at a time. First of all, keeping clients online when a gateway is lost, well, that would, generically speaking, be first hop redundancy protocols. So that would be VRRP, GLBP, HSRP, all of those are first hop redundancy protocols, and they would all apply to A. Now next, keeping control plane relationships online during an RP failure, that would be the result of nonstop forwarding. Remember, nonstop forwarding works with SSO in order to keep those routing relationships like OSPF and EIGRP online while we're failing over between route processors. So C, as we can imagine, failing between backup RPs, that would be the responsibility of stateful switchover. SSO helps us quickly fail over between RPs and keeps the data plane online during that process. Well, that wraps up this quiz. If you found yourself struggling with any of these questions, then be sure to go back and watch the appropriate videos in order to fill those knowledge gaps. Otherwise, congratulations on completing Design High Availability in Campus Networks. I hope this has been informative for you. I'd like to thank you for viewing.